So in 8.1, we spent time talking about what are polar coordinates, how to convert from polar to rectangular, and sort of like the idea that polar coordinates is just a way to describe location based upon amount of rotation and distance traveled. Today we're going to take a look at what these polar equations look like when you actually graph them. Now, I'm actually not going to put too much emphasis on this section because, to be honest, in the year 2020, if you ever had to graph anything in polar, more likely than not, you're going to reach for a calculator or use some sort of technology. So, am I going to expect you guys to be able to do these by hand? Am I going to require you to graph by hand? Probably not, but it's still good to be able to recognize some basic polar graphs. You know, if I give you a polar equation, even if you don't have technology with you, you should be able to recognize some format. Also, um, we should at least understand the idea behind graphing by hand if we ever had to graph by hand. So let's start off by talking about a few basic shapes, basic equations that I expect everyone to know. So I'll call these special polar functions. Just like how in the rectangular coordinate system, I expect everyone to know that y equals a number is a horizontal line, x equals a number is a vertical line, y equals mx plus b is a slanted line, y equals x squares are parabolas or they're quadratics. So there are just certain key types of polar functions that you should be able to recognize just by pure looking. And we'll start off with r equaling some number, right? So what do these guys look like? So for example, r equals 3. Recall that whether or not you're graphing rectangulars, polars, or some other sort of system, a graph describes all sets of coordinates that satisfy whatever equation you have. So if we were to translate this basic polar equation, this is asking you, or telling you all points where r is 3. Now recall that all polar points are of the form r comma theta. So the equation r equals 3 puts a restriction on the r, but notice it doesn't say anything about theta. It leaves theta loose, it leaves theta open. So you have to imagine on a polar graph, every single point on the polar graph that is 3 units away from the origin. And again, because it doesn't put any restrictions on theta, you have to consider all angles. So for example, at 0 radians, this guy is 3 units away from the origin. At pi halves radians, this point is 3 units away. At pi radians, this point is 3 units away. At 3 pi halves 3 pi halves radians, this point excuse me again, is 3 units away. And if you sort of just mentally go through every single angle and mark 3 units away, so for example, at 45 degrees or pi fourths radians, that's about 3 units away. This point is about 3 units away from the origin. This point is about 3 units away from the origin. This point is about 3 units away. This point. You can see that the picture that we end up making, although this is a sketch, so it's not going to be perfect, should be a circle. And that is the definition of a circle. The definition of a circle is a locus of points that are equidistant to a set center. So you should recognize, or the big takeaway is that in polar form, r equals anything, I'll use the letter A, is a circle centered at the origin with radius absolute value of a. And we say absolute value of a because, radius is a length and it should always be positive. And it is possible to have polar equations with negative r. So we just make sure that the radius is positive. So that's one of the special polar functions. R equaling a number will always be a circle with a set radius. The other type of special polar equations is theta equaling a number. For example, suppose we had theta equals, I don't know, pi third radians. Okay. And again, in order to understand or visualize what this graph looks like, we really have to read and understand what this equation says. This equation says all points where theta is pi thirds, or in other words, all points that have an angle of pi thirds. And again, if all polar points are r comma theta, this type of equation puts a restriction on theta, but it leaves r completely open. So we could have an r length of 1, an r length of 2, an r length of 1.5, an r length of negative 3. We have to take account for all of those. The only restriction, the only points that we plot, according to this equation here, is all points that have a set angle. Well, what type of picture, what type of equation would that produce? Well, if I were to draw a random coordinate Cartesian plane, and I mark down pi thirds radians. Again, I'm just going to approximate. I'm not going to break out a protractor, but I'm going to say, that looks like pi thirds radians. I have to mark. It is my job to mark down every single point that has that angle. Well, this could be a length of 1 comma pi thirds. Here's 2 comma pi thirds. Here's 3 comma pi thirds. Here's 1/2 comma pi thirds. 1.5 comma pi thirds. 2.5 comma pi thirds. 0.7 pi thirds. 2.3 comma pi thirds. You can see that every single point that has an angle pi thirds will form a straight line. But because r can be negative, technically this point here has an angle of pi thirds. That could be, for example, -1 comma pi thirds, -2 comma pi thirds, -3 comma pi thirds, so on and so forth. So we can see that these types of equations will always produce a line. So that's sort of like the idea. If you ever had a polar equations where you had theta equals some number, again, I'll just use a random letter, A, will produce a line that goes through the origin. Moreover, because we know that tangent of theta equals y over x, we know for a fact that this line will produce a line that goes through the origin we know that this line has a slope of tangent of a. It'll have a slope of the tangent of whatever that number is. So again, if I give you a polar equation that said r equals some number, theta equals some number, I don't expect you to run out to grab a calculator and figure it out. You should know off the top of your head that r equals a number is a circle, because it literally says all points that have a set radius, and theta equals a number is a straight line, because it says literally all points on this particular angle. If your polar curve or the graph isn't as obvious, then you have some work to do if you don't have a calculator. Now, here's the cool thing about graphing. It sort of is cool and anticlimactic at the same time. The technique is not complicated. We don't have to employ fancy schmancy math and calculus and whatnot. The technique that you use to graph polar functions is the very first technique you use to graph any equation back in like middle school in pre-algebra. It's simply a table of values. Remember when everyone first learned to graph, we did an XY table? Well, it's the same thing. That's the big secret. How do you graph polar functions? You make a T table. The only thing that's different is, instead of making an XY table in the rectangular coordinate system, you're going to make a theta R table because we're in the polar system. That's the big secret, right? To graph polar functions by hand, you can simply make a theta R table. For example, suppose I ask you to plot or graph, I'll change the instructions to graph, R equals to sine theta, right? So, I mean, like I said, there's really nothing special going on here. It's really simple work. You just make a theta R table. Now, just like with rectangular equations, the question I always get is, hey, Mr. Vo, which angles do we pick? You can pick whatever angles you want. Just like how when you graph rectangular equations, you can pick whatever x value you want. Pick whatever theta value you want. Now, if I'm doing this by hand without a calculator, I'll most likely pick the, quote, special angles. So, for example, 0 radians I know is special. Pi 6 is special. Pi fourths is special. Pi thirds is special. Pi halves is special. The second question I always get is, hey, Mr. Vo, how long do I have to go? How many thetas, how many angles do you have to pick? And there's probably a nice mathematical way to always figure it out, but I go, why bother doing the extra thinking? How do I know how far I need to go? I go as far as I need. So, plot a handful of points, 5, 6, 7 points, and then look at your picture. You will know a polar graph is complete when it loops upon itself. Because the independent variable to polar equations are angles, and angles are cyclical, you should know that eventually, it could be quick, it could be long, but eventually the graph will overlap itself, sort of like a snake eating its own tail. And if you don't have a complete picture, if you keep going forward and the snake hasn't eaten its tail, so to speak, you know you have more angles to go. Let's just show it with this example. So let's say, I think that's enough. I'm going to just use these 1, 2, 3, 4, these 5 points. So just go ahead, one at a time, take these theta values, and plug into the equation. Since these are special unit circle angles, I'm not going to go through the whole logic. I'm going to assume we all know how to evaluate. So I'm just going to fast forward through the y values. So if I plug a 0 radians into here, you're going to get a 0. If I plug a pi 6 into here, sine of pi 6 is 1/2. 2 times 1/2 is 1. If I plug a pi fourths into there, I'm going to get a radical 2. Plug a pi thirds in there, I'm going to get a radical 3. Plug a pi halves in there, I'm going to get a 2. Now, when it comes to graphing, you really should graph them on polar paper. You guys remember what polar paper was? It was that Cartesian grid that had a whole bunch of rings, right? Now, you could graph it on something that looks like this, but it's a bit messy and not not accurate. In an ideal world, you would have a computer-generated polar graph. And if we were doing this in class, I would give you some, but obviously we're not in class, and I don't have any to give you. So we're just gonna, eyeball it. It would be nice if you had like a protractor or something to be accurate, but hey, we will make do. So I will try to be somewhat accurate, but as long as you get the general idea, that's all that matters. So remember, although we made a theta r table, polar points are always r comma theta. So technically speaking, this is 0, 0. That didn't really matter. This is 1 comma pi 6. This is 2 comma pi fourths. But the ironic thing is, we would graph it backwards anyway. So I'm going to graph 0 radians, and I go 0, which is obviously the origin here. So next I go 1 comma pi 6, but I'm going to rotate pi 6 radians first. Now, I do have access to a protractor, so I will use a protractor to be somewhat accurate. So I know that pi 6 is 30 degrees. So here's 30 degrees, and I need to walk 1 units. Now, I can decide whatever I want to be 1. I just have to be consistent. So let's make 1, I don't know. How far do I go? I go up to 2, so I don't want to make it too big. Let's make 1 2 inches. So here's right there. Here's 1 comma pi 6. Then we got to go to, there should be radical 2, not 2. Then we're going to go to radical 2 comma pi fourths. So pi fourths is 45 degrees. Here's 45 degrees. And then I need to go radical 2. Now radical 2 is about 1.4. But I've made 1 unit 2 inches, so I need to multiply everything by 2. So if radical 2 is 1.4, in my scale, that's going to be 2.8. So here we have 1. Actually, never mind. Radical 2 is not 1.4. Let's see here. I should use a calculator. Yeah, it's 1.4, yeah. So here we have 2.8. That's 1, 2, that's 5. I'm going to eyeball it somewhere right there. Right. And then we have pi thirds, which is 60 degrees. And we're going radical 3. Radical 3 is 1.7, I think, around about there. You double him, he's going to be 3.4. So here's 1, 2, 3. Let's see. Did I do this one right? 1, 2. 2.8 right here. Man, I went way too far. There we go. So here's 30 pi thirds, which is 60 degrees, and I need to go 3.4-ish. 1, 2, 3.4-ish. I'm going to approximate there. And then we have pi halves and 2. So at pi halves, I need to go 2, which in my scale is going to be 4. So 4 inches. 1, 2, 3, 4, right there. Now notice the order in which you plotted the points. The order is important as well because that tells you how to connect the dots. So this was the first point, the second point, the third point, the fourth point, the fifth point. You have to connect the dots in that precise order. So far the shape we have is this. Now this is not a closed loop. I know for a fact that I'm not finished. The points, here's where I started. Here's where I ended. It's not connected. That tells me as a mathematician, you got more points to plot. So I'm going to go back to my theta, comma, r graph and make some more x values. And again, you can use whatever theta values you want. The smart thing to do is to use special angles. So in continuing with that line, and continuing with that thought, after pi halves, what's the next special angle? 2 pi thirds, I think. Yeah, 2 pi thirds. You look on a unit circle. Next becomes the fourths, 3 pi fourths, and then the 6, 5 pi 6, and then 1 full pi. Again, I'm not doing anything special, just plug the theta into the equation. So if you were to plug theta into the equation, plugging in a 2 pi thirds, you get a radical 3. I should continue with the color. Plugging in a 3 pi fourths, you get a radical 2. Plugging a pi 6, since it's signed, it's going to be all positive, you get a 1. Plugging a pi, you get a 0. And I hope people notice the symmetry here. So at 2 pi thirds, which is let's see here. 2 pi thirds is 120 degrees, which has a reference angle of 60. Unfortunately, my ruler only does reference angles. So here he is at radical 3, which we said in our system was 3.4 inches. 1, 2, 3. I'm going to approximate 4 there. At 3 pi fourths, which is a reference angle of 45 degrees, he is at, what's that? Radical 2, which we said in our system was 2.8. So 2.8 inches. I'm going to say somewhere right there. And then at 5 pi 6, he's at 1 inch. So 5 pi 6 is a reference angle of 30 degrees. And we said that 1 was about 2 inches here. Right there. And then at pi, which is right here, he's back at the origin because it's pi comma 0. So notice how the graph does curl upon itself. So here we have, again, my drawing isn't 100% accurate because we didn't have proper polar graph paper, and my protractor wasn't and ruler wasn't exactly 100% accurate. But if I squinted enough, it looks like we have a circle. So it turns out that when you ever have r equals some number times sine or some number times cosine, it will be a circle. That's pretty cool. Now you can get as fancy as you want with these graphs here, and by doing the same thing, making a table of values. And I would highly suggest in your practice, do 1 or 2, quote, complicated ones by hand so you get a feel for it. But honestly, I'm probably not going to quiz you or test you on graphing. I wanted to expose you to polar graphs to see that, hey, these polar graphs can these polar functions can produce pretty interesting graphs. And one of the reasons why mathematicians use polar graphs is they are able, polar graphs that is, are able to describe more complicated functions, more complicated curves than rectangulars. For example, suppose, actually, I'll do this. That's the end of the notes. I'll transfer everything to Desmos now. Suppose we wanted to graph a cardioid, right? And a cardioid is a function that's very difficult to do in rectangular form, but very easy to do in polar form. Now, if you wanted to graph using technology, I suggest Desmos. It is the thing that you can use on, AZ Merit, although in hindsight, not all of you guys will take it, if we ever take it this year. If you have a regular graphing calculator like a TI-83, 84, please talk to me in person and I'll show you how to graph using your calculator if you don't know how to already. If you have like a Casio or whatever, my suggestion is to Google it, because I'm not an expert at Casios. But to graph using technology is just type it as you see it. So for example, suppose I wanted to graph, 2 plus 2 cosine of theta. That's exactly what I'm going to graph. Or that's exactly what I'm going to type in. So in any technology, a graphing calculator or Desmos, type it as you see it. So I want to type r equals 2 plus 2 cosine, and I need to put theta. Now in Desmos, the theta is in their built-in keypad. Go to the bottom left corner and hit the ABC, and you should see theta as one of the keys there. And there you go. And you can see why mathematicians call this a cardioid, because it sort of looks like a sideways heart. Now, I suggest you go through the practice and again, just play with it. Graph a few, graph all of them, just to see what they look. I would suggest, we're going by the honor system here. I would suggest you do 2 or 3 by hand so you get a feel for them, but the rest you can just use your calculator. But you can make some pretty neat pictures. So cardioids are some number plus some number times cosine or sine. You can make clovers, you can make flowers. and flowers are produced by multiple angles. 2 thetas, 3 thetas, 4 thetas. So, for example, what if I did r equals cosine of, I don't know, 2 thetas? You can see that we made a 4-leaf clover. Right? So you can make all sorts of funky designs with polar graphs, and you can see that's the power of um, polar over rectangular. It produces way more complicated graphs than rectangulars can do. So, I mean, that's it. I will expect you guys to be able to graph them by hand if needed. It's just making a theta r table. But for the most part, just have fun with it. Just graph a whole bunch of functions and see what cool pictures you can make. For example, let's graph a limacon. Limacons look something like this. Say, for example, some number 1 plus or minus. I'll do a plus. Cos 2. Let's give it a bigger radius so we can see it. 2 cosine of theta. It's sort of like a cardioid, except because the coefficients and constants aren't balanced, it sort of overshoots itself and creates an extra inner loop. If they were balanced, if it was 2 plus 2 cosine, then it would be a perfect cardioid. Right? So you can make all sorts of wicked designs. Just have fun with it, play around with it, but understand the fundamental idea of what plotting polar graphs are. It's just rotating at all of the angles and plotting the r. It's not a complicated concept. It might be tedious to do by hand, but I hope it's not very complicated. All you're doing is rotating and plotting, rotating about various angles and plotting the radii. So let's take a look at one more cool looking picture. Let's say we put a fraction inside of the angle, say r equals cosine of 2, 2 theta, that's our flower, divided by 3. Right? We get some sort of cool designs. So, play around with it, graph a whole bunch, see what designs you can make, Google them. You can Google lots of cool polar functions, and you can make a whole bunch of cool pictures like spirals and whatnot. So that's it. That's 8.2, sort of like a little fun lesson. It's not going to be tested for me, at least, but I want you to have, get your hands dirty a little bit. Graph 1 or 2 by hand, but mostly just play around with the calculator or Desmo, see what pictures you can make.